Mesmerizing patterns you sometimes see, maybe in nature, like the way a tree branches or, a snowflake structure. Now imagine math creating visuals that are just as complex, just as beautiful. That's kind of the visual side of what we're diving into today. Julia sets.
And what's really fascinating, I think, is that these beautiful images aren't just, well, they're not just pretty pictures. They actually represent some really deep mathematical ideas that have fundamentally shifted how we understand a whole load of things.
Huge range, yeah. From like how complex systems behave to maybe even the nature of shapes themselves.
Exactly. So today we're doing a deep dive into these Julia sets, of these incredible fractal structures that came out of the work of two mathematicians, Gaston Julia and Pierre Fatou, way back.
Right, maybe names you don't hear every day, but their work, their insights, they've had a truly massive impact across mathematics. Revolutionary, really.
Absolutely. So our mission, if you like, for this discussion is to figure out how these intricate things, these Julia sets, how they drove such big leaps forward. We'll look at how a pretty simple starting point.
Like just repeating a math rule?
Exactly, just iterating a simple function, how that can lead to these incredibly complex and really profoundly important mathematical discoveries.
Okay, so get ready for a bit of a mind stretch. By the end of this, you should have a much better feel for how these, well, visually striking objects helped us understand concepts like chaos.
That sensitivity idea.
Right. Sensitivity, iteration, just repeating things, and the sort of underlying behavior of mathematical functions. And this is where it gets really interesting.
Yeah, I'd say probably the most significant impact, the most groundbreaking contribution of Julia sets is how they really changed our view of dynamical systems.
How things change over time.
Right. And chaos theory within that. Before Julia and Fatou, the idea that simple rules could lead to behavior you just couldn't predict, well, it was a bit more abstract. Julia sets gave us some of the first really solid, concrete examples of this kind of chaos.
Okay, so backing up a bit then. In simple terms, what is a Julia set in this context of, change and potential chaos?
Okay, so imagine you've got a rule, a mathematical function. A common one is f z equals z squared plus c.
Okay.
You pick a starting number, z, it's a complex number, which has two parts, and you apply the rule. You get a result. Then you take that result, apply the rule again and again and again. You build up this sequence, its orbit.
Right.
Now, the Julia set, it's like a boundary, a dividing line. If you pick a starting z on one side of this line, its orbit stays contained. It stays within a certain region. It's bounded, well-behaved. But if you pick a starting point on the other side, the orbit just shoots off, grows bigger and bigger towards infinity. It goes wild. The Julia set, usually called JF, is that exact boundary.
Yeah.
And the well-behaved regions, that's the Fatou set, FF, the stable zones.
Okay, so it's like some starting points are safe, their path stays local, others are on a runaway train to infinity, and the Julia set is the fence.
That's a great way to put it. The fence between stability and escape. And that's where the chaos connection comes in. Right on the Julia set, on that fence, you see this extreme sensitivity. Change your starting points is just a tiny, tiny bit.
Like infinitesimally.
Pretty much. And its long-term path, its fate, can be completely different. One might stay bounded forever. The one right next to it might fly off to infinity. Julia sets were some of the first things mathematicians could really point to and say, look, this is what chaotic dynamics can look like. It allowed them to study things like attractors, where orbits might settle down, repellers, points that push orbits away, and these basins of attraction, the whole set of starting points that end up heading towards the same attractor. It's like a tiny nudge can send you down a totally different valley.
That really is mind-bending. A tiny initial difference, totally different futures. Now, you mentioned that C in the function, SC, ZAs plus C. What does that do?
C. That's where it gets even more interesting, I think. Think of C like a control knob for the function.
Okay.
As you change the value of C, just tweak that complex number, the whole shape and structure of the Julia set can change dramatically, sometimes subtly, sometimes radically. These changes are called bifurcations points, where the whole system's behavior fundamentally shifts.
So C determines the specific pattern we see.
Exactly. And what's truly amazing is the Mandelbrot set. You've probably seen pictures of that too, the sort of snowman shape.
Oh yeah, the iconic one.
Right. The Mandelbrot set acts like a kind of map or maybe a catalog. It shows you for every possible C value, whether the corresponding Julia set for f say 0 plus C is connected all in one piece or not. So, studying the Mandelbrot set with all its incredibly intricate details tells us huge amounts about how these Julia sets change as you turn that C dial. It was absolutely vital for developing what we call bifurcation theory.
So the Mandelbrot set isn't just one picture, it's like a guide to all the connected Julia sets for that specific type of function.
Yeah.
That's incredible. Okay, moving on slightly, you also mentioned that Julia sets deepen complex analysis. How did that work?
Well, the functions we're talking about, like z sol plus c, they belong to a special class called holomorphic functions. These are the core objects of study in complex analysis functions of complex numbers that are essentially nicely smooth or differentiable everywhere they're defined. Now, studying Julia and Fatou sets forced mathematicians to think about what happens when you iterate these functions, when you apply them repeatedly, not just locally, like looking under a microscope at one point, but globally across the whole complex plane.
So it forced a shift from just local properties to understanding the function's behavior everywhere when repeated over and over.
Precisely. Traditional complex analysis often focused on local behavior, maybe using power series to approximate things nearby. Iteration demands a much broader perspective, and tools from complex analysis became crucial for understanding the stable parts, the Fatou set.
How so?
There's a concept called normal families and a really key result, Montel's theorem. It basically helps identify collections of these holomorphic functions that behave uniformly well. They don't do anything too wild or unpredictable in a region. And this theorem turned out to be perfect for characterizing the Fatou, sets the regions of stability where iterating the function doesn't cause chaos. The need to understand these stable regions within this iteration context really pushed the application and understanding of these complex analysis tools.
Interesting. And you also mentioned something about conformal mappings and Riemann surfaces. Sounds quite advanced.
It gets a bit technical, yeah, but the basic idea is really neat. For some Julia sets, particularly the connected ones, you can sometimes find a special transformation, a conformal map, that essentially stretches and bends the region around the plane. Julia sets smoothly onto a much simpler shape, like the inside or outside of a perfect circle, the unit disk.
Without tearing it or messing up the angles locally.
Exactly. It preserves angles locally. Think of it like smoothly morphing the complex shape onto a standard, well-understood one. This is incredibly powerful because it lets mathematicians use all the tools and theorems they already have for simpler domains, like the unit disk things from conformal geometry, theory of Riemann surfaces.
Which are like idealized surfaces for complex functions.
Right, and apply that knowledge back to understand the intricate structure of the original complicated Julia set. It's like finding a way to translate the complex problem into a language we already understand much better.
Okay, that makes sense. Use a known map to explore unknown territory. Brilliant. Now, fractals. We mentioned Julia sets are key examples, but you also said Julia and Fatou were doing this before Mandelbrot coined the term fractal.
Yes, and that's a really crucial historical point. Benoit Mandelbrot did amazing work popularizing and formalizing the concept of fractals much later, in the 70s and 80s. But Julia and Fatou, back in the 1910s, were mathematically describing and analyzing these incredibly complex, self-similar structures.
Structures that look similar at different zoom levels.
Exactly. That self-similarity is a key feature. Their work provided some of the very first rigorous mathematical frameworks for dealing with shapes that weren't the smooth lines and curves of classical Euclidean geometry. They were grappling with the kind of irregular, fragmented complexity we actually see all around us in nature long before it was fashionable.
So they were mathematically seeing these infinitely detailed shapes decades before we had the word fractal.
Pretty much, yes. Julia sets provided a concrete way to analyze these irregular shapes, and it connects to this idea of fractal dimension or Hausdorff dimension.
Where things can have dimensions that aren't whole numbers, like 1.3 or something.
Right. This concept allows us to quantify the roughness or space-filling nature of these sets. It turned out to be incredibly relevant for Julia sets. Figuring out the precise Hausdorff dimension of a given Julia set became, and still is, a really significant and often difficult research question. It pushed mathematicians to think beyond simple integer dimensions.
It really is amazing they were laying this groundwork so early. Now, obviously, the pictures are stunning. How did computers change the game for studying Julia sets?
Oh, dramatically. I mean, the sheer intricacy of these sets, exploring them in detail, was almost impossible before computers. Think about it. You have to apply the function millions, maybe billions of times for points near the boundary to see where they go.
Just computationally infeasible by hand.
Completely.
Yeah.
So the need to actually see these sets, to plot them, directly drove the development of algorithms for iterating complex functions efficiently and mapping out the behavior of points. It was a huge early motivator for computational mathematics.
So the desire to visualize the math actually spurred advancements in computation itself.
Absolutely. And then the visual complexity of Julia sets and the Mandelbrot set, too, of course, they just captured the imagination, didn't they? They became these iconic images.
Yeah, they were everywhere for a while. Posters, book covers.
Exactly. And that popular interest fed back into research. It helped generate interest in funding for computer graphics, for scientific visualization. People wanted better ways to render these things, which pushed technology forward, better algorithms, faster processors. It was this wonderful feedback loop.
Math-inspiring visuals. Visuals demanding better tech.
Right. And maybe even more importantly, mathematically speaking, computers allowed for numerical experimentation on a massive scale. Mathematicians could explore visually how sets changed, spot patterns, form conjectures, educated guesses.
Based on what they were seeing on the screen.
Precisely. And then they could go back to traditional methods, pen and paper, rigorous proof, to try and prove those conjectures were actually true. This interplay between computation, visualization, and formal proof became a really powerful new way of doing mathematics.
Fascinating. Using the computer almost as a research partner, not just a calculator. Now, beyond these main areas, dynamics, complex analysis, fractals, computation, do Julia sets connect elsewhere in math?
They do. The connections spread out quite widely, sometimes in surprising ways. For example, there are links to number theory.
Really? How does number theory connect to iterating complex functions?
Well, if you look at iterations of polynomials where the coefficients are rational numbers or maybe algebraic numbers, questions about the distribution of periodic points.
Those points that cycle back to themselves after a few steps.
Exactly. Questions about where those points are, what kind of numbers they are, turn out to relate to deep questions in number theory, especially concerning algebraic integers and related structures. It's quite intricate.
Wow, okay. Didn't see that coming. What about topology? You mentioned connectivity earlier.
Yes, topology, the study of shape and continuity, is fundamental. We already talked about whether a Julia set is connected one piece or totally disconnected, like dust a Cantor set. For FEZ equals Z is sought plus C, that connection is incredibly direct. The Julia set JF is connected if and only if the parameter C is inside the Mandelbrot set.
Ah, so the Mandelbrot set isn't just a catalog, it's a topological decider for that family.
Exactly. It's a beautiful deep link between the dynamics where C lives and the topology, the shape of JF. This bridge between dynamics and topology has been a huge area of research.
And lastly, you mentioned measure theory about the size of sets.
Right. So often for these kinds of functions, the Julia set itself, technically speaking, has zero Lebesgue measure.
Meaning it takes up no area on the complex plane, like a line has no area.
Kind of like that, yes. Intuitively, it's infinitesimally thin. But as we've seen, these sets can be incredibly complex topologically and geometrically. So even though their area is zero, they're far from simple. This forces mathematicians to use more sophisticated tools to measure their size, like the Hausdorff measure we mentioned earlier.
Which can capture that fractal dimension, the roughness.
Exactly. It gives a way to assign a meaningful size that reflects the set's complexity, even if its area is zero. It shows that our standard notion of size isn't always sufficient for these intricate objects.
So even being small in one sense doesn't stop them from being incredibly rich and complex, needing advanced tools to grasp them.
Precisely. It's another example of how studying Julia sets pushed the development and application of tools across different mathematical fields.
Okay, so let's just recap the journey here. Julia sets, they weren't just pretty mathematical art, they were fundamental. They gave us concrete examples of chaos in dynamical systems.
Huge for chaos theory.
Right. They pushed complex analysis towards a more global iterative view.
Definitely stretched the field.
They were basically proto-fractals, laying groundwork for fractal geometry before the term even existed.
Pioneers in describing complexity.
They drove computational math and visualization forward because people desperately wanted to see them.
Major catalyst there.
And they even built unexpected bridges to number theory, topology, and measure theory. It's really quite a story.
It really is. It shows how these abstract mathematical constructs, just emerging from iterating simple rules, can have these incredibly deep, far-reaching consequences across so many areas of mathematics. Unexpected insights popping up everywhere.
It just makes you wonder, doesn't it?
Yeah.
About the sheer power and, the beauty you can get from simple repeating processes. And it kind of leaves you thinking, where else might simple rules be generating incredible complexity, maybe right under our noses? Something to ponder, perhaps, after our dive today.